Hello, happy Kumarapunan. Yesterday we saw in a double negative medium or left-handed medium why the index of refraction or refractive index will be negative, and as a consequence of negative refractive index how the Snell's law is affected. In the Snell's law we saw that the transmitted angle becomes negative. Now we'll see some of the consequences of negative transmitted angle when using Snell's law. So today we'll discuss that. Now that we'll discuss based on optical principle. What happens is, suppose we have a right-handed medium. So from this source, if it is a denser medium, the right-handed medium is a rarer medium and the source is in the denser medium, then when the wave propagates from the rarer medium to denser medium, then in the denser medium the ray will bend towards the normal, which is shown by the green, right? So the green part shows you how it happens, what happens when the propagation is from rarer medium to denser medium. Similarly, the opposite happens when the wave propagates from denser to rarer. It will go away from the normal in the rarer medium. So this is the normal optical principle that happens in the medium, in any optical medium. Suppose instead of optical medium we are considering a electromagnetic medium. The same principle happens also in the electromagnetic medium. You can see below there are two simulations. The left hand is denser to rarer. If you see, the source is the red portion, which is the maximum value is red, minimum value is blue. So from blue to red, red to blue, that occurs cyclically. So that is the source. From this source, the wave is propagating. The source is in the denser medium. It is propagating to the rarer medium. At the boundary where we have drawn the z-axis, at the boundary you can see the wave is bending away from the normal. If you look at the rarer to denser medium, which is on the right hand side, from the source it comes there, then it is bending from uh, bending towards the normal. So since it is bending towards the normal, it is like uh, it is converging. So that is in the denser medium, it is converging. In the rarer medium, it is diverging. That is what you see. Now let us see, replace the right-handed medium with a left-handed medium. So if we replace the right-handed medium with a left-handed medium, then if we travel from rarer to denser medium, then the problem will be different. Or if we travel from denser to rarer medium, then the problem will be different. Now, before considering that, let us consider the total internal reflection. Now, in the total internal reflection, what happens is you incident a wave from a rarer medium to a denser medium. It is right-handed medium. The denser medium is right-handed medium. incident a wave from rarer medium to denser medium below or beyond a critical angle. So the angle of incidence is more than the critical angle. So it has to be more than some angle which is called the critical angle. If it is more than that angle, then it will come back to the rarer medium. Instead of going into the denser medium, it will come back to the rarer medium. So it is called reflection. So, and since it is a phenomenon because of the right-handed medium, which is not a reflecting surface. In the right-handed medium, on the instead of refraction, reflection is occurring. This is called total internal reflection. That you can also see in the simulation. We have a right-handed medium in which we are doing the simulation. You can see from the rarer medium, it is coming towards the denser medium, and at the interface, it is going back. So the green portion that is going back, the wave which is getting reflected at the plane ZY plane, it is getting reflected at the ZY plane. So from the x-axis it is coming normally and it is getting reflected at the ZY plane. This we have taken from a paper on microwave theory and technique. Next. Now let us look at the magic that happens when we use the left-handed medium. So here you see we have on the left-hand side air for which n is equal to 1. On the right-handed side we have any medium for which n is equal to small n. So which is right-handed medium. Now if we incident a wave, so angle is theta 1, this will be refracted giving us an angle theta 2. Theta 2 is the transmitted angle, so theta t or theta 2 you can say that angle, and this angle you can say theta 1 or theta I. So this is what happens based on Snell's law. So Snell's law says that n will be equal to small n will be equal to sine theta 1 by sine theta 2. This is as per the Snell's law. So if you have a right-handed liquid in a glass and dip a stick into the liquid, it will appear as if the stick has bent towards the right-hand side. So if the stick is put into the liquid from the left-hand side, in the liquid it will appear as if the stick is bending inside the liquid towards the right hand side because of the refraction, because of the phenomenon of refraction in the right-handed medium. If the liquid is right-handed liquid, which means the refractive index is positive in the liquid. Now let us see the other case. So other case is in the air, it is we have n is equal to 1 on the left hand side. Right hand side is a LHM medium in which the refractive index is minus n. So in that case theta t becomes is negative, so theta 2 will become now minus theta 2. Since it is becoming minus theta 2, you can see that what happens to the liquid, to the stick which is deep into the liquid from the left hand side. It bends, instead of bending towards the right hand side, it bends towards the left hand side. So this is one consequence of the negative refractive index. Next. Here, because of Snell's law, n is equal to minus sine theta 1 by sine theta 2. Since theta 2 is negative, so sine theta 1 by sine theta 2. Sine theta 2 is negative, that is minus sine theta 2. So we get this. So this is shown by Victor Vasilev in one of his fundamental papers published in 1968. Next. Now suppose we have a source in negative refractive index media, NRI media is negative refractive index media. Now, if we have a source inside the negative refractive index media, what will happen that we are seeing here in the simulation. So it will, when it comes to the RHM medium or right-handed medium or positive refractive index medium, which is beyond the YZ plane. So in the YZ plane towards the x-axis is the source. So from the source it comes towards this plane to beyond the YZ plane. Then you can see how the wave is propagating in the right-handed medium. As it comes from the left-handed medium, you can see how it is propagating in the right-handed medium. Next. So and also you can see the other part, which is the backward wave propagation. You can see from the source always wave propagates outward, but because we have negative k, so you can see here the wave is propagating towards the source. In the negative medium or in the NRI medium, the wave is propagating towards the source. That is one effect that we see here. Next. Then the radiation is converging. In this case, it is converging. Always if it is from the negative medium to positive medium, it is converging. If it is from positive medium to negative medium, sorry, from positive to positive medium, it is always diverging. Whereas if it is from negative to positive, it is always converging. So we have got a converging radiation that you can see in the medium 2, the wave is converging. Next. Now let us see uh, a slab, a slab of negative refractive index. If you see a slab of negative refractive index, so the slab depth or the slab width is D. The thickness of the slab is D. That is what we see here. Then we are having a source on the left hand side. From that we are incidenting wave with angle theta 1 onto the slab, which gets refracted with negative angle theta 2. So this distance is A. When it goes to theta 2, similarly on the this we have shown in the upper side, lower side also it will be with negative theta 2, so they will meet at a point which is f1 inside the slab. So A is the distance of the source from the surface of the slab. A dash is the distance of the focus point f1 from the surface of the slab. Now f1 acts as a source. From that waves are diverging. So and at the other end of the slab, they will again converge. They will start to converge. They will converge to the point F2 in the outside the slab. The distance from F1 to the slab surface is B dash, and from slab surface to the focal point is B. Our total distance from the source to F2 is X. Let us remember this. From this, we will do some calculation next. Now we know N, which is the refractive index, is sine theta 1 by sine theta 2. Now sine theta 1 by sine theta 2 is approximately equal to tan theta 1 by tan theta 2 when theta 1 and theta 2 are small. Now theta tan theta 1 by tan theta 2, that we can easily find out to be A dash by A or B dash by B. So N is equal to A dash by A, which is also B dash by B. Next. Now look at the figure. From this you can say A dash plus B dash is equal to D. We already know N is equal to A dash by A. So A is equal to A dash by N. Similarly, B is equal to B dash by N. This we know. Next. Now find out what will be the X. X, which is the focal distance, that is X is equal to A plus A dash plus B dash plus B. Now for A we will put A dash by N, for B we will put B dash by N. So if we put that, then we will get A dash by N plus A dash plus B dash by N plus, B dash by N plus B dash. So then you take uh, uh, 1 by n common, or they have this n terms if we can take common, then that is A dash plus B dash by n. A dash plus B dash is D, so D by n. What is remaining? A dash plus B dash, that is also D. So X is equal to D plus D by n. So from this what we understand is, you take a normal slab, simple slab, that is focusing the source on the other side at a distance of x, which is equal to d plus d by n, where d is the thickness of the slab. So say simple slab acts like a lens because of negative refraction in DNG medium. Next. So with that, we come to the end of our discussion for today. And in the next discussion, we'll end our topic, negative refractive index, completely. Thank you.